First. So, all right. And so we are continuing with the symmetric group, well, basically the group of permutations. So we will be talking about the permutations again. Especially we are interested in this symmetric group because at least we need the notation. And there are some certain aspects related to the group theory that we need to investigate. So let's remember that Sn is the set of all permutations. We think of these as functions of that send this set to that set, but it's an invertible function, so therefore it's also onto. And so we consider all permutations as functions on that set. It's not just a sequence of numbers, but it's just a function. And so as a result, the composition of these functions is the group operation in here. And the order of the group is n factorial, obviously. And then we have this cycle notation. I said that this is going to be very useful for us. So we just have these cycles for each permutation. So this permutation changes 1 into 3 and 3 into 4 and 4 into 1. So we just, this is basically a 3 cycle. There are also 1 cycles as well, but usually in the notation, we suppress the 1 cycles and just write down the only the non-trivial cycles, right? Let's just remember this. So in any case, a permutation that consists of a single 2 cycle and 1 cycle for the rest is called a transposition. We are going to use this expression a lot. So as a result, a transposition is basically a permutation of that form. It just transposes I and j. So if I just compute, show this diagram in here, it just changes the I with j and j with I, but everything else is basically a 1 cycle. So everything else is a 1 cycle. So this is 1, 2, and whatever. So in any case, so that's the basic permutation, basically. It's in a way, the smallest permutation. And so one result in here that's of importance is this, this theorem. I'm just going to write a theorem in here. So let me say it like this. Every permutation, I mean, it basically says that you can express every permutation. You can obtain every permutation as a sequence of transpositions, basically. Every permutation can be written as a product of transpositions. I don't know. I mean, this is an example, perhaps. So think about this permutation that sends 1 into 2, 2 into 3, and 3 into 1. So that's 1, 2, 3. I think perhaps I can do this like 1, 3, 1, 2 permutation. Can I do that? Let me actually check this. So this is a permutation that sends first 1 into 3. No, that's not the correct one. So sorry about this. I'm changing the notation. So that's, I wrote this because I didn't have any idea what I'm writing. So I'm writing the correct thing in here. So the first permutation transposition changes 1 into 2. The second one keeps the 2 constant. All right, so therefore 1 is converted into 2. How about 2? First permutation converts 2 into 1. Second one sends 1 into 3, so therefore 2 is sent into 3. And whatever. the first one doesn't change 3, the second one changes 3 into 1. And so therefore, yeah, that's basically 1, 2, 3. Okay, so as a result, for example, this 3 cycle can be written as the product of these 2 transpositions. I can also write it down in other forms, like, for example, 2, 3, 1, 2, sorry, 2, yeah, that's true, right? 2, 3, 1, 2. Just check this, for example. So as a result, the expression is not unique, so you can use transpositions of different order. And sometimes you can even, I don't know, do things like this, for example, 1, 2, 1, 3, 1, 2, 1, 3, for example. And so as a result, you can perhaps write it as a longer sequence of transpositions following one another, right? So, but the important thing is that you can express every permutation as a product of transposition. So I think this is quite straightforward. We can easily show this easily. There's no problem with this. The problem and the difficult part in here is the other part of the theorem, right? Right. So that basically says this, right? Suppose a permutation G is expressed as a product of transpositions. I mean, there are these 2 alternative things, like, for example, let me write it down like this. So there are m terms in here, and the other one has, I don't know, let's call it like h1 and dot, 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 and hm prime. So there are different number of terms in here. Okay. All right. So let me say it like this, right? This is Fi, Hj, these are transpositions. So this is the second theorem, right? That's also a theorem. Then this says that the m minus m prime is even. I don't know if this is the correct way of saying this. Well, that's the correct way of saying this. What I would like to say is that basically if m is odd, then m prime is odd. And similarly, if m is even, then m prime is necessarily even. So here too, I mean, we can express this as a product of 2 transpositions or 4 transpositions. The difference between them is always an even number, which means, right, say it like this. If, let's say it like this. M is odd if and only if m prime is odd. And if m is even, if and only if m prime is even. Let me express it like this. People usually express it like that. So as a result, if you can express a permutation as a product of, let's say, an odd number of transpositions, then in all of the other alternative expressions of that permutation, we always express it as an odd number of permutations. And you can kind of see that this evenness and oddness somehow is, has this natural product nature. So for example, if I multiply an odd permutation with another odd permutation, I need to get an even permutation, for example, and things like that. So as a result, this is the definition of the, this is the definition. So we call a permutation G as odd. We call it as odd if G can be expressed, can be written as a product of an odd number of transpositions. Let me write it completely, so as a product of an odd number of transpositions. And then let me not repeat the same thing and then say that similarly for even, right? So we say that a permutation is even if it can be expressed as a product of an even number of transpositions. Okay, so as a result, we basically described it. We basically classified all permutations into these two kinds, even and odd. And so as a result, we have this. There's also some kind of a thing that we call as the signature of a permutation. So I'm going to call this as epsilon g, or sometimes people show it with -1 to the power g, actually. Don't worry about this. This is just a notation, all right? So that's either +1 or -1. So basically, we say that this value is +1 if g is even. It's an even permutation. Well, whatever. So it is -1 if g is odd. Okay. And so as a result, this is something that we actually use a lot. So I'm going to then talk about a few places where we actually meet, like in determinants, for example. But let me just go ahead and then say something more about this. All right, so the first thing is that signature is a homomorphism. I think that's what we need to say. So this function from the symmetric group to the group of numbers +1, -1 together with multiplication is a homomorphism, right? So that's a theorem. Think of it like this. It's a theorem. But to prove this, let's say it like this, I'm just going to leave that to you. Show that the signature of a product of two permutations, let's say, I don't know, g of h, for example. I mean, the product of two permutations is equal to the product of these signatures. Just show it however you want, all right? But this is kind of obvious because of the definition. So if you think of the signature as like this is the -1 to the power m in here, right? In that expression. So evenness or oddness is basically decided on the number of transpositions in an expression. So as a result, this is somewhat natural, right? Just show it. I'm going to leave that to you. All right, which means there's a kernel of that. Let me quickly call this, right? The kernel of epsilon is like the even permutations in Sn. So we can consider only the even permutations in that case. So that's a subgroup. It's actually a normal subgroup, but it is obvious that it is normal because if a subgroup, the number of elements in a subgroup is just 1/2 of the group order, then obviously there are only two cosets, and so therefore the left coset and the right coset must be identical. In any case, so this is called AN, and it's called the alternating group. I don't know why this name is given. But I can give some further examples of such groups actually. And since basically this thing only has two cosets, right? Itself and the set of all permutations, odd permutations. So you can easily see that the order of the alternating group is basically 1/2 of n factorial. So that's the order. So alternating group is just one example of a permutation group. I mean, it's a group formed from permutations. So for now, I'm just going to define this as a name. I don't have any physical examples of uses of such groups, except that when time comes, I may actually tell you some examples about this. So signature is a homomorphism. All right, that's good. There are a few things like all transpositions are even. Are odd. I'm sorry about this. Right. So any element, any group, anything in this form is odd, is an odd permutation. Okay, so that's the first thing. The second thing, we have done this example before. So this 1, 2, 3, I said that I can express this as this product in here, right? So therefore it's a product of two transpositions. So therefore, this 1, 2, 3 is an even permutation. Okay, so a 2 cycle is odd, but a 3 cycle is even. So as a result, this is what I'm going to say in general. So an n cycle is an odd permutation if and only if n is even. So just try to remember that these two are opposite to each other. So probably a 2 cycle is going to help you. 2 cycle, well, 2 is even, but somehow this is an odd permutation because I know that the 2 cycle is a transposition. So every transposition can be written as a single transposition, obviously. So it's an obviously odd by definition. And you can show that an n cycle like this, for example, this is like 1, 2, 3, ... n. Doesn't matter what it is. I can express this as 1, 2, 1, 3, 1, 4, ... 1 n product. And you can easily see that the number of terms in here is basically n minus 1. N minus 1 transpositions in here. It's not n, it's just 1 less because somehow I'm using 1 in each of these expressions in here. So as a result, if I use a transposition, then 1 together with some other label. So the other labels are n minus 1 in number, right? That's, you can kind of understand it like that, okay? So as a result, this is the general rule in here. So as a result, for example, I can look at S3 in here. So it consists of identity, these transpositions, 2, 3, and then these 2, 3 cycles, right? You can easily see this. I'm going to write it with a colored thing like that. So these are odd permutations. And well, these are even. Identity, identity has to be even. So you can think of it as a group element obtained by 0 transposition, or I don't know, a transposition is always opposite to itself. It's an inverse of itself. So therefore, I can write the identity as a product of 2 transpositions, basically. So that's also even. So let me kind of show it in here. I don't know, with a gray color like that. So when I say identity, I can express it as like 1, 2 product with 1, 2, because I know that these, the inverse of this one is this, so therefore their product is equal to identity. And so therefore identity can be written as a product of 2 transpositions, so therefore identity is even. Okay. In any case, so therefore in this case, for example, the alternating group is formed from the identity and the 3 cycles. So that's the alternating group. So it's a 3-element subgroup of S3. In any case, we are going to meet signature, for example, for that special group, but for all other symmetric groups as well. We are going to see the signature as, it's a homomorphism, but you can think of the result plus minus 1, not just as a number, but a 1-by-1 matrix. So therefore, it will be a representation, actually. So as a result, this is something that we are going to see a lot later, because we will be doing this representation theory. We will be finding representations of that particular group a lot later. Okay. So I don't know if you have any questions in here. Okay. There's another thing in here. An alternative way to compute the signature, to find whether a permutation is even or odd, compute the signature of a permutation. If you remember, we had this tabular form, a permutation of n objects. If you remember, that there was this kind of a thing in here. So in the tabular form, we just write down in the second row in here, we are going to write down the values of the to which element does the permutation send this element to whatever. All right, that's basically what we are writing this thing now. And then I have said that I can think of this sequence of elements as an alternative way of expressing the permutation. And so as a result, for this reason, some people think the permutations as sequences and not functions. I said that, well, don't do this. For several reasons, the function point of view is very valuable. In any case, by just looking at this, I can decide that sequence. I can easily decide whether the permutation is even or odd. So let me just say it like this. So I'm just going to look at 2 elements in here, right? Like F1 and F3, for example. So the thing is something like this. So we say that, let's say, I'm going to say if I is less than J, right? I'm looking for the situation. So we say Fi and Fj are in order if Fi is smaller than Fj. And we say that these pair of numbers are out of order, if Fi is bigger than Fj. This is too abstract, so as a result, I'm just going to do an example in here. So suppose my example is this. So F is this function. So 1, 2, it's a permutation of 4 elements. Why 4? I don't know. Let's call it like this is 2, 3, 4, 1. Doesn't matter, right? So what I'm doing is like I'm looking at the sequence in here. Let's just concentrate on that sequence. And so as a result, I'm just going to write these sequence in here. I don't even need to know these things in here. So I just need the order in here. So what I do is like I look at these 2 elements in here, and decide if they are in order or out of order. So for example, this 2 and 3, this is in order. So that's also in order. This is out of order. But do not compare two successive elements. So for example, these two are in order, and so on. So in any case, what you do is, I'm just going to do it like that. What you do is, you just go over all of the pairs in here and just mark all of the out of the order pairs. So for example, this is out of order because 2 doesn't come before 1. It should come after, so therefore this is out of order. That's also out of order, and that's also out of order, right? So what you do is like count all out of order pairs. Count them. And so there's a number in here. Call this number. Number of out of order pairs is like, I don't know, let's call it as M. So we say that the permutation is even if M is even. Sorry. If and only if that number of out of order pairs is even. Okay. So that's the rule. So that's an alternative way of computing this. So I'm just going to write in here yeah, this is just an example. So as a result, this is going to be an odd permutation. And I don't know, for example, if G is like that, so that's just a very huge example. Let's say 6, 1, 5, 2, 3, 4, for example. It's just arbitrary. I just need to look at these, all of the out of order things. So for example, 6 is out of order. So therefore, I mean, 6 is the largest element, but somehow it appears as the first. So as a result, we have these 5 of them in here. And then I know that this 1 is in order. So therefore, just forget about this. This 5 is out of order with these, with all of these pairs. So there are 3 more in here. I think 5 plus 3, we have 8. 2, 3, 4, this is in order. So therefore, this is like 5 plus 3 is equal to 8. So therefore, this implies that G is an even permutation. Okay. I don't know if you have any questions in here, but let's talk about this Levi-Civita tensor. Levi-Civita tensor in n dimensions. Okay, so this is basically a signature, but I'm going to write it down like this. So this is a number that depends on, that has n indices. So therefore, this is a tensor of n indices. So that's a tensor of nth rank. Sorry, tensor of rank n. It's a rank n tensor. So here I1, I2, and In, these are basically numbers from 1 to n. Some of them can be repeated, but in any case, the value of the Levi-Civita tensor, if you remember, I1, I2, dot, 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 In is, let's start with 0. If any 2 indices are repeated, any 2 indices are repeated, and plus 1 if, I mean, this I1, I2, In sequence, if none of the indices are repeated, then this is a permutation of 1 to the n, right? So let's say it like this. If I1 to I to the n, whatever, this sequence in here is obtainable after n by an even permutation of 1 to n, all right? Let me say it like this. So if is an even, let me write it correctly. So is obtained by applying an even permutation to 1 to dot 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 n. So I have the standard sequence 1 to the n, and whatever. I have the standard sequence. So if I obtain, by applying a permutation to that sequence, if I obtain this thing, I would like to know if the permutation that I used in here is an even permutation or an odd permutation. Okay. So it is -1 if dot, 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 dot. It's the same thing, right? But this time this is an odd permutation. Okay. So in any case, basically what I'm going to say is this. So this Levi-Civita tensor in that case is equal to the signature of the permutation, where F is the permutation that permutes all of these numbers in that way. So that's the tabular form. And so this Levi-Civita tensor is basically the signature of that permutation, right? So in a way, this tensor somehow expresses the signature, but just keep in mind that it's a tensor, so it also has the 0 values as well. But that's not a signature of any kind of a permutation. So as a result, this Levi-Civita tensor is a little bit more than a signature, but when it is non-zero, it is equal to the signature of some kind of a permutation. Right, so as a result, you can then find the signature by just looking, by using that rule, for example. So I know that, for example, epsilon 1 to the n is equal to +1, obviously by definition, because this basically corresponds to the identity permutation. And let's say it like this, epsilon I1, I2, dot, 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 In is a completely antisymmetric tensor, which basically says that it changes sign if any two indices are exchanged. In any case, in permutation language, this is basically a transposition is applied, right? Transposition is applied. And we know that transposition is an odd permutation. So under a transposition, the signature changes sign, right? So if you just add one transposition, then the signature changes sign. So that's essentially this property of being completely antisymmetric is basically consistent with this. So let's remember these, for example, epsilon 1, 2, 3. That's epsilon 3, 2, 1, 3, 1, 2, and epsilon 2, 3, 1. So these has some nice cyclic order in here. So as a result, I mean, we get used to writing these things down. So as a result, if these three numbers are in cyclic order, then the Levi-Civita tensor is 1. But they are not cyclic, so like 1, 3, 2, 3, 2, 1, and it's the anticyclic, where in the opposite order, they have the correct order, right? So that's epsilon 2, 1, 3, so that's equal to -1, and whatever. So the other ones are where there are repeated indices, this is going to be equal to 0. All right, so I just want to add this. So for example, this feature only happens if the dimension is odd. If the dimension is even, we don't have this. So for example, I know that in 4 dimensions, because in 4 dimensions we use Levi-Civita tensor a lot, because the space is 4-dimensional, right? So it is defined like that. That's the natural definition. But epsilon 4, 1, 2, 3, this is not +1, that's equal to -1, even though they have the same cyclic order. So moving 1 to the front doesn't, well, it basically changes the sign, right? And you can easily see this because to move 4 to the front, I need to carry out basically 3 transpositions. So first I need to move to that location, then to that location, and to that location, right? So I need 3 transpositions, so therefore this is obviously -1. And yes, so let me say it like this, etc. So as a result, in these kind of situations, you have to be very careful. Do you have any questions about this? Okay, this is something that's extra, but I would like to also, sometimes I talk about a determinant of a matrix. So let A be an n by n matrix. So I'm going to use this kind of a notation. So this is like A11, A12, and so on. So as a result, there are these indices in here. So Aij is the ijth entry, right? So in any case, the determinant is something like this, the determinant of A. There is actually a general formula. I don't know how you compute determinants, but in any case, let me express it like this. What you do is like, you take one element from each row in such a way that you also have chosen one element from each column. So you basically pick elements from rows and columns in such a way that you only choose one element from each row and one element from each column, right? But you can make this choice in many different ways. Apparently, you can make this choice in n factorial different ways. So as a result, this choice has something to do with permutation, and people usually write it down like that. So for example, if I choose on the first row, this is the element that I have chosen. So in general, I can write this thing down as like on the first row, let's say that the element that I have chosen is A1, A1. A1, I1, right? Let's say that in the second row, I'm choosing an element, let's say A2, I2. So for example, it is this element in here, A21. But in any case, so as a result, I choose elements for each row. And the claim in here is that, of course, all of the row IDs in all of these entries should be different, and they are different because they start from 1 and end up in n. Moreover, all of these I1, I2, and In should also be different. And so therefore, this is just a permutation. So what we do is, we just sum this, but we also multiply it with the Levi-Civita tensor. Okay. And then sum over all I1 to In. So that's the definition, is an abstract definition of a determinant, the determinant of a matrix. So somehow this thing also enters into that picture, into that mathematical concept. I can also express it in terms of the permutations. So as a result, this is not a summation over indices, but it's a summation over permutations. So let's say that F is a permutation in Sn. So I'm going to write in here as the permutation, the signature of the permutation multiplied with, this time I'm going to basically I'm really permuting the column index in here. So as a result, instead of I1, I'm going to write f of 1. That's basically the image of the entry 1 under permutation. So we have A2, let me use a comma in here, f of 2, and an f of n. So as a result, you can kind of see that there are n factorial expressions in here. Whatever, so I can also carry out, write down each term like that. This is basically the inverse of the permutation applied on the first index. And so as a result, some people just write down this expression with the rows and columns exchanged. And instead of doing the summation over the inverse, we usually do it as the summation over the this expression in here. So that kind of tells you that you can basically remove the inverses in here. So as a result, this basically corresponds to the fact that I just defined the determinant by using, I mean, instead of considering the permutations as the permutations of columns, I consider it as the permutations of rows, basically. But I don't want to explain it in detail in here. This also corresponds to the fact that a matrix and the transpose of the matrix have the same determinant, okay? Whatever, so this is some extra information. So if you are confused about this, just forget about it. It has nothing to do with our course. I just wanted to mention about this since we have mentioned about the Levi-Civita tensor. Right, I mentioned the Levi-Civita tensor because it's something that we meet frequently in physics. You know the places you meet in 3 dimensions, but also in, I don't know, in relativity too, you meet these kind of Levi-Civita tensors with rank 4 basically. So these are frequently used. Okay. One more thing, sorry. Any subgroup of Sn is called a permutation group. So alternating group is an example, for example. The group Sn, the symmetric group, is a permutation group because every group is a subgroup of itself. But basically, a permutation group is a group formed from permutations. Okay, so this is an interesting theorem. So any group, any finite group, well, I'm going to give the order actually in any case. Any finite group G, sorry about this, let me start it in the more appropriate way. So that's called the Cayley's theorem. A group of order n is isomorphic to a subgroup of Sn. Okay, a group G of order n. So whatever the group is, I don't care what it is, but it has to be a finite group. It has to be a finite group because the number of elements in the group is going to be important. In that case, we will be talking about the permutations of n objects. So somehow it tells you that there's some kind of a homomorphism from the group to that Sn such that this is 1-to-1, right? Phi is 1-to-1. So that means the group G is basically isomorphic to its image, the image of that homomorphism. And that image is basically as a subgroup of Sn. So that's a permutation group. Right? This implies that You can think of any group as actually a permutation group on an abstract sense. Any finite group, right? Mathematically, this says that the symmetric group is very complicated because somehow every symmetric group, I mean, these symmetric groups contain all the other finite groups as subgroups of themselves, all right? So as a result, if there is a very complicated finite group, then the same complication should actually be apparent for the symmetric group too. Okay, so that kind of tells you that the symmetric group is somehow contains everything in a way. So as a result, these are kind of the most difficult groups to study. And so as a result, this is actually kind of an interesting result. The proof is very simple because this is something that we have done before. So that's something called a rearrangement lemma, if you remember. So let's say G is an element of the group, and then we have said that G multiplied with G is equal to G. Or it basically says this, so let's say G is equal to some, let's say that I list the elements of the group as, I don't know, these sequence of n elements. In that case, G multiplied with G, we have said this is basically is the set of these products. We have argued before that all of these entries are different from each other. So as a result, what you get is the same group, but arranged in a different way. So as a result, for example, this entry in here is basically the group entry in the I1th place, for example. This is the group entry in the I2th place, and so on. This is the group entry in I-nth place. Okay. So as a result, let's say it like this, let multiplication by G is equivalent to a permutation. I'm just going to write down the, sorry about this. I'm going to make it a little bit smaller so that the whole thing is on the screen. So this is the permutation I-n. So left multiplication by a group element is equivalent to a permutation. Okay.
By equivalent, do we mean can be represented as, or
can be represented as, yes.
Okay.
I can then write this thing down like this. So it's a formula: G multiplied with Gi is equal to G of phi I, right? There's some kind of a permutation, right? Phi is a permutation of, let's say, the set of indices 1 to n. But you can think of these as the group entries as well. You don't have to call them as like 1, 2, and you don't have to call them as numbers. So this is a permutation. Just keep in mind that phi depends on the group element in here. And so as a result, I would write, for example, instead of phi, I'm going to write phi of G in here. So as a result, I would use the equation like this: G multiplied with Gi is equal to G of phi of G applied on I, all right? So in any case, so phi of G is a permutation. So that's an element of Sn. If I have a left multiplication with another group element in here, so I know that this is equal to H applied to G subscript with this index in here, whatever that is, let's call it as, I don't know, J, for example. It doesn't matter what it is. Yeah, so therefore this is G of the permutation associated with H applied on phi G of I, right? I don't know if you understand what I'm doing in here. So this is an index, let's call it as J, and I'm saying that H multiplied with G of J is equal to G of left multiplication with H basically changes the indices. So therefore this is phi H of J, right? And that's what I'm writing in here. So that means I can rewrite this as, by using associativity, as Hg multiplied with Gi. And supposedly this should actually give me the element in the place where there's phi Hg is a permutation of this. And somehow, therefore, these two permutations, or the effect of these two permutations, should be the same. Right? So therefore, this implies that permutation, when I left multiply with Hg, is the same thing as the permutation first when I multiply with G, and then we apply the permutation when we multiply with H. Okay, so as a result, the group order, I mean, I have some kind of a permutation, I have some kind of a function in here. So for every group element, I have a corresponding permutation in Sn, right? So as a result, this phi in here is a map from the group elements to the permutations. And this map satisfies that property. So therefore, this says that phi is a homomorphism. I mean, phi is a map from, yeah, whatever. Try to understand this, all right? And then you need to show that phi is one-to-one. So this is the next step. Show that phi is one-to-one. What does that mean? It means this, right? If G is different than H, then the permutation that I would get when I left multiplied with G is different than the permutation that I would induce if I left multiplied with H. Okay, that's what it actually means. So basically, in that case, that means that the kernel of that map is the identity. So only the identity element corresponds to the identity permutation. Yeah, whatever. I mean, try to understand it like that. All right. So there are a few things that I need to say, all right? Because we are going to meet this later. So this is very important for us. We are going to basically use this thing to find a matrix representation of a group in terms of permutation matrices. This is called a regular representation. It will be very critical at some in one of the proofs, right? So that's why I'm just spending time on this. It's not just an I don't know some kind of a mathematical theorem that we can forget about. No, we are going to use it at some point. So therefore, I'm stressing on this. So Cayley theorem is something that I'm going to remind you next week. All right, let me then stop here. Stop recording.